In the previous practical, you used heritability equal actual genetic variance divided by phenotypic variance. Then you got the estimated heritability and compared to the expected heritability, right? But in real situations, you cannot observe actual G. So you need a family design that I showed in the lecture, right? So from the design, then you know what is sample correlation from the design, and you can observe phenotypes. Therefore, you can estimate phenotypic correlation. So from the design, you can estimate heritability from this equation. So let's have a look at the code in the sheet dash simr. Get this. Yeah. So uh, probably before you start, probably you want to change the total number of seed pairs. In this case, seed pairs is 1,000, 10,000. Then probably your code, I don't know what value in your code, but you need to change any value to the 2. So assume you have a 2, one pair of from each family. That's what this simulation does. So let's go through this code. So we simulated heritability as 0.3. This is true simulated heritability. And sample correlation, first we give 0.5. So this is like a full SIPs or digit twins. So from this, we know what is true heritability, right? That's what we simulated. And sample correlation is 0.5. So this is just to compare as your estimation and true heritability. So and now we now making design. So the total number of SIPs in the sample is 10,000, and number of members within each family is 2. So like twins, right? So digit twins. Then the mean of phenotypes assigned as 0, and you give heritability for the genetic structure. Then covariance between two seed pair is function of heritability and sample correlations, right? And this is a symmetric matrix. Therefore, this and this is the same. And also the second digit, the twin, also has the same heritability, right? And this is assigned as genetic structure to here. Then genetic value is simulated from multivariate normal distribution. This is number of record, and this is the mean, and this is the genetic structure according to this code. Okay. Then residual values. Now that is 1 mass heritability, right? This is residual. So in this case, phenotypes are standardized, mean 0 and variance is 1. And for the residuals, there's errors. Errors shouldn't be correlate between SIPs, right? That's why this is assigned as 0. And this is residual is the same as the first and second, the digit twins or the full SIPs. Okay, now this is the residual structure. So this is a residual structure. And EV, there is a residual value. It's come from multivariate normal distribution. This is the number of record, and this is the mean, and this is the residual structure here. Okay. Then the phenotypes is according to the equation V equals G plus E. So that is the sum of genetic value and residual value. Okay, then so because you can now from the simulated data or real data, you can observe phenotypes for the first and second digit twins or full SIPs. Therefore, you can estimate phenotypic correlations, right? And also because you know sample correlation that is 0.5 as assigned in the simulation code. Therefore, this phenotypic correlation divided by sample correlation is heritability. Okay, that's what this code is working. So we can try with this code, give a source and give the name, then try. So as we simulated, true heritability is 0.3, and sample correlation, because we design as full SIP or DZ twins, that's 0.5, and phenotypic correlation from the simulation Y1 and Y2 is 0.166, and this divided by this, the sample correlation is 0.333. So this is estimate heritability from this design, right? Does that make sense? So and this within this bracket, this is kind of confidence interval because all estimation has the standard error as well as 95% confidence interval you can estimate. So this shows the confidence interval. Let's briefly have a look how to get this confidence interval. Uh, so how does it? So that is from the yeah, this function. That is correlation dot test. Then from the coefficient from this function actually give 95% interval. That is from this. Okay. So first question is what is mean value for uh, the phenotypes for the first SIP? So we can simply give a mean and y v dash 1. This is for the phenotype for the first mean, right? Then that will give close to 0 as expected. That's what we simulated. Also probably it's the same, very similar for the second SIP as well. That's close to 0, right? Then what is the variance? So let's have a look. The variance for the first SIP is close to 1. Is that what you simulated? We can check it out. So easy one. Yeah, because we simulate the genetic value according to the genetic structure. The variance is heritability, right? Then also residual is 1 minus heritability. So sum of this one is 1. That's why phenotypic variance is close to 1. Did that make sense? Also for the second C has similar, right? That's 1. So let's have make a histogram for the first C. Give a hist y1. Where is histogram? Yeah, looks like this. So this is a mean 0 and the variance is 1 around here. So this is around 1 standard deviation interval. So this is variance. It looks like this. Okay. So also you can have a look what is the maximum number for the y1. First the SIPs phenotypes, that's 3.6. What is the minimum value of the, that is minus. Then also this is 10,000 record for each SIP, but you can probably comparing the first 10 record. Sorry, the other way around. So 1 to 10. Yeah, so this is the first sieve, and this is the second sieve. Then, so you can see this is from first to 10th family, and first twins, digit twins, and second digit twins. So actually, the phenotypic correlation is correlation between this vector and this vector, right? So you can do correlation y we 1 to y we 2. So this is phenotypic correlation, right? Then this divided by, because you know these two vectors sample correlation is 0.5. So divided by sample correlation give the estimate heritability, right? That's what you show before here, okay, with this confidence interval. So this confidence interval actually include the true heritability, right? 0.3 is between here. So the estimation is quite unbiased given that the confidence interval.